Hello there and welcome. So we are going to learn how to use Kicad to design PCBs, and in this video I'm going to show you how to install Kicad and also tell you a bit about Kicad. So just open your browser and Google Kicad or Kicad. Some people say Kicad, others say Kicad. So just choose one that sounds well and stick with it. So Google Kicad, as I would call it in the course, and just click on the link that leads to www.kicad.org. So over here, it's their homepage, and it's going to tell you a bit about the software. You can read on it, but in summary, it's a free open source software for designing printed circuit boards, which is also known as PCBs. And if you do not know anything about PCBs yet, I'm still going to teach you what a PCB is, so don't worry. We want to focus on how to install it. So on the page, you see a download link that is based on your operating system. I am on a Windows machine, so you can see that it's highlighting for that, but it will also take you to a place where you can select the platform on which you want to install. So if you're on Windows, you download for Windows. If you're on Mac, you download for Mac. Linux, you do the same. And there is also a version that runs inside of Docker. I am on Windows. So what I'm going to do is to click on Windows here, and it's going to send you to the downloads page where you have a list of sites that you can download from. Usually it is grouped by continent, and you have to choose the server that is closest to you. I am in Germany at the moment, so I'm going to choose Europe from Switzerland, CEN. And once you come to this page, you can see that download has already started. This donation here isn't compulsory, but if you do have the means, please do go ahead and download, donate something to support the good cause. So you can see from my downloads site that it is actually downloading Kicad. So I'm going to end this video from here, and once the download is complete, I will install it and we will start going through. Okay. Hello there and welcome back. So with the download completed, all you have to do is to go to the folder into which you downloaded the Kicad setup and double click it so that we can go through the installation. I have done so, and so I'm just waiting for it to show up, then we can go through the process. All right, so this is it. It's the usual Windows installation setup flow. All right, we never read, we just go next. But this one is important. It's asking, do you want to install it for everyone on your system or just for yourself? I'm selfish, so I'm going to say install just for me. If you're generous, install for everyone else. And over here, just make sure you've selected everything. We are starting, so I don't want us to be selective. Having everything is better than later needing something and going through different processes to add it up. And you choose a location where it should be installed. Usually the default are fine, right? So you just click on install, and at this point installation has started. So just like I said, it's like every normal Windows installation. And so I'm going to stop the video here, wait for it to finish, and then we can continue in the next video. Thank you very much for watching this, and I will see you in the next. Hello there and welcome back. So at this point installation is completed and I have started Kicad for the first time. Usually when it's your first time installing Kicad and you start it, it's going to ask you to make some choices. Usually just choose that it should start with the default settings or options and everything should be fine. Once you do that, you are going to see this screen here, and it looks very simple, right? But Kicad is a really powerful software and we are going to learn everything about it. On the start page, it shows you a list of tools and other things that you can do. So on the left, we can click to create a new project, and we can also click here to open a project. We can archive a project, we can unarchive a project. You understand what that means. We can refresh it so that the listings here will be refreshed, and we also have browse project files. There will be content here as we begin to create different projects. Okay, so for now it's empty because we do not have any project created. Now on the right, you can see different tools. There is the schematic editor, for capturing your schematic, the schematic of the circuits that you want to design the PCB for. There's a symbol editor. So in the schematic capture, we use circuit symbols to represent physical components that will have to sit on the PCB, and these symbols have to be created somehow. And even though Kicad ships with a huge library of symbols, sometimes it becomes necessary for you to create your own symbol, and in that case you use the symbol editor. There's also the PCB editor. So the workflow is such that you start by capturing your schematic using the schematic editor, and then after capturing the schematic, you use the PCB editor to do the actual layout of the physical structure and connections between the components on your PCB. So in that case, you use the PCB editor to design the actual PCB from the schematic that you captured from here. There is also the footprint editor. So the footprint is the physical representation of the dimensions and the paths that the components are going to take when placed on the PCB. And just as you can create symbols, you can also create footprint. And the good thing, once again, is that Kicad ships with a huge library of footprints. But like I said earlier, sometimes it becomes necessary that you design your own footprint, and in that case, you're going to use the footprint editor. There is also the Gerber viewer for viewing Gerber files. Gerber files are some of the output kind of files that you can generate from Kicad and you ship to the manufacturer for manufacturing. So we'll get there. And then there's image converter. So sometimes you want to put images on your PCB, and it becomes necessary for you to convert the image into a format that can be used in Kicad, and that is when this image converter tool comes in. There is a calculator tools, as you can imagine, for calculations specific to PCB design. There's a drawing sheet editor that also you can always see down here that there's a kind of help message. So it says edit drawing sheet borders and title blocks for use in schematic and PCB design. So very self-descriptive. And there is also the plugin and content manager. This is where you can add plugins. So like I said, Kicad is an open source software. It ships with tools that you need to design PCBs, but people also create plugins that extends the capabilities of the software. Some of the plugins are plugins that can help you to order your PCB directly from manufacturers such as JLCPCB or PCBWay, plugins that does auto routing, and many more plugins. Okay, so we will explore all those options. This is just the welcome screen that you see when you start Kicad. Thank you very much for watching this. In the next video, we will create a project so that we can take a look at some other details of Kicad. I will see you in the next video. Hello there and welcome back. In this video, we're going to take a look at how to create a project in Kicad. And it's simple, right? So you can click on this icon here that says new project. You can also see the shortcut key. It's a combination of Control plus N, right? So if you press Control N on your keyboard, you should be able to execute the same objective, or you can also come to file and then click on new project. So for the same goal, there are three different ways of accomplishing this. And so it says project template selector. There is the default Kicad project template, API series, Arduino Mega. So we will talk about project template. What the template do is it kind of bootstraps the project so that it is easier to accomplish certain things. So for example, if I'm working with Arduino Nano, it says this template forms the basis for a board with the same layout as the Arduino Nano, right? So it's just commonly designed kind of PCB layouts that they have already made into template for you to use. If you do not know what you're doing or you want to start from scratch, it's always okay to choose the default Kicad project template, right? And you can click OK here. And so what's going to happen is you have to give your project a name. Usually it has to be in this project folder. I already have a project that I created. That is why it came here. But you want to give your project a name. All right. So let's call this Hello PCB because it's going to be the first PCB we'll design. Very simple, not complicated, just so we learn our way around the Kicad software. And so it's going to create this folder. And as you can see, it has created a Hello PCB Kicad project here, and inside of it there are two files. There's the hello pcb.kicad underscore sch. That is a schematic file. That is where you are going to do your schematic capture. And there's the hello pcb.kicad underscore pcb. This is where we do the actual design of the PCB. So that is it for this video, just showing you how to create a project without doing anything complicated. In the next video, which also begins the next chapter, we will actually begin to learn about schematic capture. Thank you very much for watching this, and I will see you in the next video. Hello there and welcome back. So in this video, I just want to show you what a printed circuit board is. And I know that is quite an unnecessary assumption, because you should already know what a printed circuit board is before you are interested in learning how to build them. But just for the sake of education, I'm going to show you this. So we all know that printed circuit board is a flat board that simply mechanically supports and also electrically connects electronic components, right? So if you look at any electrical gadget, you look inside of it, it is very likely that you see these green boards. There are different colors, but most of the time they are going to be green, and then you see the electronic components sitting on it, and then there are wires created on the flat board that connects the different electronic components together. So instead of using individual wires to connect parts, a PCB uses this thin copper pathway. So these are the wires, right? They are taking the places of wires, right? So it uses the thin copper pathways, which are also known as traces, that are printed or etched on the board, right? So I want you to think of a PCB as a road network of an electrical device, and the traces are just the road networks that is moving signals from one electrical or electronic component to the other. And the main part of the PCB is the substrate, which is also the base material, which is usually made from a particular type of fiberglass known as FR4. And there are copper layers. So usually there are 2 copper layers, but you can have more. You can have 4, 8, 16, 32, and even more, right? And so these copper layers are where the etching happens in the manufacturing process to create the traces that becomes the pathways along which signals travel. And then we also do have parts. Parts are the places on the PCB where we attach the component to. We also have vias, which are tiny holes that connect the copper layers in a multi-layer PCB. These are all things that we are going to spend time looking at. There's also the solder mask, and there's also the silk screen, which is where we see all the printed labels showing the component names, numbers, and assembly information. So like I said, I assume you already do know what a PCB is, so I don't want to spend too much time on this video. Thank you very much for watching this, and I will see you in the next video. Hello there and welcome back. So in this chapter, we are going to learn how to perform schematic capture. And like I explained earlier, the workflow is such that you capture schematic, and then out of the schematic you are going to design the PCB. So I'm taking the project we created earlier, the Hello PCB project, and once it's opened you will see that there are 2 files, hello pcb.kicad underscore sch, that is for the schematic, and then there's hello pcb.kicad underscore pcb, that is for the board itself. We are going to focus on the schematic, so you can double click this, and you give your computer a while, right? Because it's the first time you have installed Kicad, it might take some time for it to load. But once it has loaded, you will see that you are greeted or you are met with this schematic editor window. All right, so the way Kicad works is that each tool usually opens in its own window, and so many times it's important to have multiple screens when you are doing some really serious PCB design. It won't be long before your single screen or monitor isn't gonna be enough for all the kind of things that you want to do. All right, so this is the schematic editor window, and this is where we do what is known as schematic capture. And what happens in schematic capture is usually for every electronics hardware that you want to build, you do have a circuit that you want to actually make the PCB out of. And the workflow again is that you capture that circuit using the schematic editor that is known as the schematic capture. That process of using the schematic editor to kind of draw your circuit is known as the schematic capture. And what I've seen so many courses do is they will usually teach Kicad by taking you through all the tools up here, and then they'll come here, and then they'll come to the right. We are not going to do that in this course. The reason I'm not going to choose that approach is that it makes video courses unnecessarily long. Instead, what I'm going to do is I will teach you how to use a tool as and when it becomes necessary. And trust me, by the time we are done with this course, you will know what to do with everything that is in here. Okay, so let's just focus on the title block. But before we do that, let me show you how you can navigate around in Kicad or the schematic editor. It's important that you have a mouse that has the middle mouse button or the wheel, right? Because I can use that to zoom in and out by scrolling in and out. So as you can see, as I move my mouse in and out, it is scrolling, right? And I can also use the same middle mouse button. I just click and hold, drag, and then I can pan around. So you can see that I can pan around my sheet, right? So this is the sheet. This is the area where we are going to capture our circuit. And when I click and hold the middle mouse button, I'm able to pan it around like you can see. Okay, so you use the middle mouse button to scroll in and out, and that is going to be zooming. And then you can also just pan around. There are also buttons here that you can use to do the same. So I click this and it makes it bigger. I click this, it makes it smaller. And there's this zoom to fit, which is going to zoom the capturing area so that it fits the screen real estate area of your monitor. And there are other tools that you can also take a look at. So this is just the schematic editor. And just to see around, at least you know how to pan, how to move and all that, right? So in the next video, we are going to take a look at what is known as the title block and how to change things in it. Thank you very much for watching this, and I will see you in the next video. Hello there and welcome back. So in this video, I want us to focus our attention on just this area of the schematic editor, and this is known as the title block. We can bring it into focus by hovering our mouse pointer over it and using the middle mouse button to scroll to zoom in, and this is the title block. So in Kicad, the title block is the information panel that appears on the schematic sheet. So this is our sheet, okay? Like this whole thing that you see here is our sheet, but this section of the sheet is what is known as the title block. So it's the information panel that appears on the schematic sheet and PCB drawing, and it stores important metadata about your project and helps identify and document your design. So as you can see, there are important metadata information here, like the title, which is usually going to be the about the project. What is it that you are doing? There's also the size of the sheet, A4. You can change it if you need bigger or smaller, the date, and also the revision, right? And it can store a lot more information. So typically the Kicad title block contains fields such as the project title, like I showed you. It also has information about the company or the organization or individual who created the design. It also has information about the revision number. People choose, let's say, V1, V1.1, V1.2, or people also do Rev A, Rev B. It depends on how you have chosen to name different versions of the same project or circuit, or how your team agrees to do the versioning. Okay, there is also the date information, when the design was created or when it was last updated. You can store that here. There is also information about the author, that is the name of the engineer that did the design. There's also the sheet number if it's a multi-sheet design. So you can see that this is ID 1 of 1. It means it is just sheet 1 in just one sheet. All right, if we had multiple, it's going to show. And then you can also add comment. And why is the title block useful? It's useful because it helps project identification, version control, documentation, team collaboration, and manufacturing, and also maintenance. Okay, so whenever I speak of the title block, or any PCB designer who uses Kicad or any other PCB software talks about the title block, this is what you need to imagine in your mind. And so there is a way we can modify the information in the title block by going to File and then clicking on Page Settings. Okay, usually when you are performing any action, look for the corresponding icon also on the toolbar, so if I come to File, Page Settings, I see this icon here. What it means is that I can also click on this same icon here, and I'm going to get the same dialog, or be able to accomplish the same thing. Okay, so here you can see that we can fill in our title block. For example, we can type the date manually, but we can also click this and it's going to insert today's date. Revision, if I want to call this, let's say, Rev A, I just choose Rev A. The title, I'm just gonna call it Hello PCB. It should be anything that is descriptive enough. I'm gonna call this Mechatronics with Pi, Mechatronics with Pi, but I mean your company name. And then there are comments here. So each comment field has a place that it appears on the title block. It requires that you play around with it to see which comment appears where. Okay, but the most important ones are the ones that I have also filled in here. And you can also change the size of your sheet. Like I said, there's A5, A4, A3, A2, A1, A0, and all sort of different sizes. For this video, A4 is okay, so I'm going to maintain that. You can also change the orientation, either landscape or portrait mode, and you understand this easily, needs no explanation. So I'm going to click on OK here, and you can see that the title block has been updated with the information that I entered in the page settings. So you come to File, Page Settings, or you can just click on this icon here. So you see why I didn't want to spend time taking you through all the icons in the toolbar and everything. Like I said, we'll use them as and when they are necessary. So now you know about the title block and how to edit it. Thank you very much for watching this, and I will see you in the next video. Hello there and welcome back. So now that we know how to edit the title block, the next thing we are going to do is to learn how to actually capture our circuit. Okay, and to do that we need to add symbols. I explained that I don't even need an explanation here, right? You know that every circuit is made up of circuit symbols, and each circuit symbol has a corresponding physical component that it represents, right? So schematic capturing is literally you translating that circuit you have on paper or in your mind onto the schematic editor in Kicad. This is all we call schematic capturing. And to do that, you need to place symbols. So if you come to the right hand side here, you can see these icons here. We are just going to focus on this particular one. It's called place symbol. Okay, so if I click on it, you see the choose symbols, and look at how many symbols Kicad ships with. 22,784. It's more than enough for you to be able to build almost any circuits that you want. And if for some reason the symbol you are looking for isn't included in the default library, then you will be able to use the symbol editor tool to create your own symbol. This is also something that we are going to learn about. Now, so let me show you another way you can bring up this symbol, place symbol or choose symbol dialog. Okay, so the first one is we clicked on this icon here and it brought it, but look at something. When you hover your mouse, you can see that it says place symbol and it has put the shortcut key in bracket. It says A. So what it means is that even if I don't click this, I can just press A and it's going to achieve the same. One other thing that I want you to note is that when you select a tool in Kicad, it is sticky. What it means is that your mouse pointer, look at my mouse pointer now, it has turned into the choose symbol tool, and it's going to be so until you press the escape key on your keyboard. That is what I mean by sticky selection. Okay, so you see that this time around I'm not coming to click on the place symbol, but right wherever I am, I'm just going to press A, and that has already activated the choose symbol dialog. In the choose symbol dialog, you can also see that the symbols are grouped into what is known as libraries. Okay, and down here you can check this check mark to place repeated copies. What it means is that if I select a particular symbol and I place it, it is going to be a sticky selection. So if I click again, it's going to place it, and click again, it's going to place it until I do not want to do that. It's useful when you want to place multiple copies of the same symbol. Okay, so the symbols are grouped into libraries. So you can see there is audio amplifiers here. There are different audio amplifiers. There are things that are symbols that are grouped under analog. Okay, and when you select any symbol, you will see the symbol here, how it's going to look in your schematic, and the footprint, that is how it's actually going to look on the PCB, is also going to be shown down here. The footprint isn't always available, but in the choose symbol dialog, you will always find the appearance of the symbol as you will see it in your schematic. Okay, so there are also comparators here, like some common op-amps. So you can see that these have been carefully grouped into libraries to make it easy for you to find what you are looking for. And it's not an easy task. Making 22,000 items easily searchable and grouped is a great job, and I think they've done really great here. Like you see microchip, there's pick 12, pick 10, pick 16. So if you know you're going to use any of the picks, you know where to start from. However, there is also the filter app here, so I can start by typing in, let's say, resistor, and you can see that it filters down to the component whose name you have typed. You are not always going to get it because sometimes the way they name them are different from how you're going to search, and this takes some practice. Look at it, like I said, you aren't always going to get a footprint assigned to a symbol, especially if the symbol has several different types of footprint. Then it becomes your job to select the particular footprint. So this is a generic resistor symbol. There is also the US symbol, which uses the zigzag line to represent the resistor. You can also search for, let's say, capacitor. So you see there's a C small US, so the US symbol for capacitor. There's a bigger one, there's a generic capacitor, and then there's also one for the polarized capacitor. So very common components that you can search for. If I search for battery, you can see that there is a battery here, there is also a cell here. So I cannot teach you how to search, right? You have to play around and then see what helps you to get what you want. And usually this comes with practice. Okay, so let's design a very simple PCB that is made up of an LED, a resistor, and a battery. Okay, so because we already have this battery here, I'm just going to click, and then you click OK, and I'm going to click. So you can zoom in whilst you still have the symbol selected, but it is not placed yet. Okay, it is not placed yet. Look at it. I can zoom in and still move around. I can zoom out and still move around. It is not placed yet. And I can also I can click the middle mouse button and continue to pan around if I want to. But if I release, then I can place it. Okay, do not sweat too much about where to place it for now. Of course, aesthetics is important, especially when it's a complex circuit, but this is a very simple circuit that we are designing, so do not worry so much about it. So you can see that we are still in the place component mode because of what you see on my mouse pointer. So if I click, it means I'm going to place a component again. Let's place our LED. So I just search for LED, and you can see that there are different kinds of LEDs. There's the A, B, G, R, and different kinds of them, right? So I'm just going to select the generic LED device. At this phase of the schematic capture, most of the time it doesn't matter the variant of LED that you choose. It is the footprint that really matters, because that is what determines the physical attachments to the actual PCB. All right, so this is an important thing we are going to learn here. I selected the LED, and as you know, the LED's positive side should be connected to the positive side of the battery, and the negative side to the negative side of the battery. But our LED here is not oriented that way. You can see that the negative side is facing the left and the positive side is facing the right. So what you can do is to press the R key, and anytime you press it, it's gonna rotate it 90 degrees. Okay, so look at how it is. I press the R, it gets rotated, it's rotated. So I think it's rotating counterclockwise. So you can keep pressing the R until you have it oriented in the orientation that you want. Okay, so look at it. I'm going to drop it somewhere here, and then the next thing I'm going to do is I want to put a resistor here, right? So I'm going to click again, and I'm going to search for R for resistor. You can choose any, whether US or the generic resistor. Maybe let's use the US resistor here. And again, we need to rotate, so I'm going to press the R to rotate it, and I'm going to put it somewhere here. Okay, now there are some other tools that we can use in our schematic capturing that is going to help us. This small crosshair, look at it. It gives you these two lines that helps you to see when two symbols are perfectly aligned. So if I choose this, I can see that, okay, the LED and the resistor are perfectly aligned. So you can always toggle between having this kind and some different types. So there's this, and there's also the 45 degrees one. Okay, so I'm going to go back to this. Always note that they are there, and then use them as and when they are necessary. So now we have placed all the components that we need. We need a battery, we need the resistor, we need the LED. Remember, at this moment we haven't set the values, they are not important yet. What we are going to learn next is how to connect them using the wire tool. Okay, so thank you very much for watching this, and I will see you in the next video. All right, so a symbol is made up of different parts, And so when it comes to moving them, there is a skill to it. Otherwise, you will move a part of a symbol when you intend to move the entire thing, or the vice versa. So let's see how to move. If I click on just the R1, which is the symbol designator or the component designator, it's telling me this is resistor 1, this is LED 1, this is battery 1, BT1, D1, R1. They are called component designators, right? If I click just on that and I drag, you can see that I'm moving it around because its position is inconsequential to the actual PCB. Like the position of these designators are inconsequential. On the PCB, you can also move them and then position them properly. So you can move them. I can also click on the value. So if I set this resistor to be, let's say, a 10K, this is what is going to show the 10K. At the moment it's showing RUS. All right, so I can click on that and move it also around somewhere. Okay, let me just bring this back to where it was, and then I can click on the resistor itself and be able to move the entire thing. However, you can also just use the M key. So if you hover your mouse over a component and you press the M key, it's automatically gonna select that, and then it's going to help you to move the entire thing. So look at it. The same thing applies to the individual parts. So if I hover over the D1, which is the designator, I can move it. If I come to the value and I press the M, I can also move just that one. So it depends on where you are hovering your mouse, right? But if I click on the symbol itself, I press M, I can be able to move the entire thing. So let's position this thing. I'm going to just rotate this and make it this way. Not because it's necessary, I'm just showing you different ways you can use to lay out your symbols in the editor. Okay, so this is it about moving, and in the next video I'm going to show you how to add wires to connect these together. Thank you very much, and I will see you in the next video. Hello then, welcome back. So we have to connect wires to the component to form the circuit, right? And to do that, you come to the right hand side here. You can see there is this tool called draw wires, and you can see that the shortcut is W. So what it means is that I can either click this tool and begin to draw wires, but you see you cannot just draw wires anywhere. I'm pressing escape and I'm going to press the W key, but you can see that I can begin to draw wires anywhere. So it depends on how you activated that tool, right? But the most important thing is you draw wires from these rounded sides of each of the symbols. Okay, so with the wire tool selected, I can click on this. You don't need to hold and drag, right? I'm not holding down my mouse, I'm just dragging the mouse without holding the left mouse button. If you get to the point where you want to branch into, you can just branch. Look at it, you don't need to click or anything. But when you get to the point where you want it to snap, you just click and it snaps there. So we have connected the right side of the resistor to the positive side of the LED, and we are going to do the same. So with the wire tool still selected, remember it's sticky, I can come here and then connect this side of the battery. There are other ways you can also establish electrical connection between symbols without necessarily drawing wires. They are called labels, and we will take a look at that later. And to complete the circuit, I'm going to connect the negative side of the LED also to the negative side of the battery, and this completes our circuit, right? So I'm going to save this, and over here you can see that we have that simple LED circuit that we have designed. In the next video, we are going to take a look at some other things that you need to do before we can actually begin to create a PCB out of this. So thank you very much for watching this, and I will see you in the next video. Hello there and welcome back. So in this video we have a complete circuit, right? Like in all sense of correctness, we have a complete circuit here. There is a voltage source, there is a resistor, there is an LED, and the polarity has been respected. So if this were a real circuit, current should flow and the LED should turn on. But I'm just making this video to show you one common misconception that people do have. So you usually see that they often add labels for VCC and ground, and it isn't necessarily correct, and it isn't the fact that you always need VCC and ground, right? um Especially when the circuit is already complete, the VCC and ground that people usually add are just called net labels. They are not physical components, and so that instead of drawing wires everywhere, you can use the net labels to connect other parts. Let me explain what I mean. So if you come to the place symbols, under 8 there is the place power symbol. So it's a similar component, just that this one has symbols that are dedicated for power. All right, and what people usually do is that if, let's say, they want to use a 5-volt battery, they will search for 5-volt like this. You can do 5-volt, and it's going to give you this net label. We'll talk about net labels, but it's just a way of helping you establish electrical connections on your schematic capture without drawing wires. And for some reason, I see people will always, let's say, because the battery has to be 5-volt, they'll take this net label, put it here, or they can also put it anywhere. And then by the way, to bring out the power symbols chooser, you can also press P. So add symbols is A and the power symbols is P. And what they do is they also search for ground, and they'll look for the ground symbol. They'll put it somewhere here, and then now they will choose the wire to connect from here to here and also here to here. This isn't absolutely necessary, and it isn't also wrong to do it here. The reason is it is inconsequential to the circuit. These are called labels, and in complicated circuits, we use labels to avoid having to draw wires all over the place, and we will see that. Okay, so I'm just going to leave this thing here, just because it is likely that whilst watching some YouTube video or some video elsewhere, you might see people do it. So I just don't want you to get confused, but I've explained to you it isn't always necessary, except you really need these labels to help you connect other areas to your circuit without drawing too many wires. Okay, all right, so this is it about this video. I just wanted to clear that misconception, and in the next video we are going to learn about the next step in the workflow. Thank you, and I will see you later. All right, so just having a completed or a complete or a functional circuit isn't enough to begin designing a circuit board. All right, so you can see that our component designators, of course, the automatic, there's PT1, there's R1, there's D1. Sometimes you wouldn't get them to be as sequential as you see in this simple circuit, and the reason is that this circuit is simple enough that we didn't delete symbols that we added earlier. Otherwise it will interfere with the component designators assignment. But there is a tool here. It's called Annotate Schematic, right? We need to always annotate our schematic, and what it's going to do is it's going to go through the component and assign designators to them. And there is how you can control the annotation. So you can give it a scope of the entire schematic, or just the current sheet, or just selection. You can just select a part of your schematic by left clicking and dragging over, and you can look at all of these options. The numbering, do you want to start from 0, 1, or whatever? These are just basic settings that you can set, and then keep existing annotation. Like if you have already annotated and you added some new symbols and you want to re-annotate, do you want to keep the existing or you want to reset? These are all options that you can do. And if there are, once you click annotate, is that tool is going to run and it's going to annotate every symbol on the circuit, right? And if there are errors or warnings or anything, it's going to tell you down here. So I click annotate, and it says annotation complete here. You can see that error 0, warning 0. This is what we like. So you just click close. All right. And this is just about the annotation, but you also want to assign actual values to the component. So this is R1. What is R1 supposed to be, right? This is D1. Okay, yeah, D1 some is okay. And this is a battery. Maybe you want to specify the voltage that you want to use here. Okay, so to do that, you can just click on the particular symbol, and then you can press the E key, which brings up this symbol's properties, so that you are able to modify properties of your symbol. So you can see the reference or the designator is R1. You can change it if you want. It isn't wrong that you change the reference or the designator after the annotation tool has run. Annotation tool is just an automated tool for assigning references, but you are free to change them as you want. What we want to see is the value, right? So let's say we want to use a 470 ohm, right? So I just do 470. Usually you can just type 470. People also like to add the R to show that it's just 470 ohms. And if it is kilo, you just K, mega, M, and all that, right? So it's just a matter of personal preference or your team's preference, most importantly if you are working in a team. So you can just assign the value and you click OK. So now you can see that it is showing 470 ohms. Here maybe we just want to indicate that we want it to be a red LED, so I can just type red in here. It doesn't really matter for an LED. The value is inconsequential here. All right. And then we also have the battery. What can we change? Instead of battery cell, I press the E, and I can maybe just type 5 volt to indicate that it's supposed to be a 5 volt battery. I don't know if we do have something like that, but this is just a simple circuit. So in this video, I have shown you how to do reference annotations and also certain values. Thank you very much for watching this, and I will see you in the next video. Hello there and welcome back. So in this video we are going to learn about footprint assignment, but before we do that I want us to talk about what footprints are. So in Kicad, footprint is the physical representation of an electronic component on the printed circuit board. So it defines where and how the component will be mounted on the board, right? So remember, this is just the schematic, but when we go to the board, we are actually at the physical layer. We are designing exactly how the board should look physically. So a footprint usually includes parts, that is where the component leads or terminals are soldered. There is also what is known as the silk screen, that is the markings that show the component outline and reference designators such as D1, R1, BT1. So all of these are going to appear on the footprint. There's also the courtyard, that is the outline that indicates the minimum space needed around the component for manufacturing and assembly. This is very important. So when we get to the PCB design properly, you don't want the courtyards of two components to cross into each other. That will make it difficult or impossible for the robots that do assembly in the manufacturing plant to do their work. So you want to respect that. It also has an assembly which outlines how it is used in the fabrication documentation. There's a 3D model association. That one is optional. So if a component or a footprint has a 3D model, then when you view the PCB design in 3D, it will look like the actual PCB with the actual component mounted onto it. I know this is a lot, and so let's go ahead and do the footprint assignment, and we'll see all the things I've spoken about in due season. So up here there is a tool known as the assign footprints. All right, and so it says run footprint assignment tool. So Kicad is made of tools and tools and tools, right? So I click that and this dialog appears here. And you can see that on the left we have the footprint libraries. So the same way that we have symbol libraries, we also do have footprint libraries, and they are grouped. So this is capacitors SMD. So if I click on, let's say, capacitors SMD, you can see that on the right there's a filtered footprint. So on the left is the footprint libraries, on the right you get the filtered footprint that matches your selection on the left. So if I go to connectors, you can see that I'm getting connectors in here, and in the middle, that is the footprint assignment itself. It is showing all the components or the symbols that we have in our circuit, and then we will be able to select them and do the assignment. But you can see that when I select battery, I'm not getting anything shown in here. Why? Because on the left I have selected the connectors library, right? And so there are these tools options up here that helps you to filter. So look at this, it says use symbol footprint filters. So if I click on this and then I click on any of them, let's say this, and you go to battery, it's going to list them. Usually the easiest is to combine this and this. So you can see that if, let's say, I click on the batteries and the batteries are here, it comes. So let's look at them properly. It says filter footprint list by pin count. All right, so if this is selected, it's going to look at what happens. If it is not selected, the list here is different, and if it is selected, it is different. So look at the tooltip to understand what it does. It says filter footprint list by pin count. So it's going to filter. So this is the selected footprint libraries, but the filtering here is going to be based on pin count. But we have selected another. It says filter by library. So what it means is that what we see on the right is based on what we've selected on the left. All right, so there's also a tool that needs some getting used to, and the most difficult part is knowing which footprint to use. Okay, imagine we've selected battery, and you can see that there are a lot of footprint for batteries in here. And so this is also a skill that you develop as you work often on creating PCBs. It is not something that anybody can teach you. With time, you get to see that they stick into your mind. But for beginners, I'm going to show you what you can do as a beginner. So if you select a particular footprint, you can right click and then do view selected footprint, and this thing is going to pop up here, and so it's going to show you. Remember, the footprint the footprint is the physical representation of the component on the PCB. So what you see is actually what you get, right? So this is what it is going to look like on the PCB, and if you want a 3D view, you can click on the 3D view thing, and then you see how it's going to look. So this is how it's going to look sitting on the PCB. So what you do as a beginner is to continue to click, select view, and then you see that you do not like it. You just have to continue selecting and checking. Maybe I like this one that I'm seeing here. So I want to use a coin cell battery, and I can see that this one is already beginning to look like what I want. There is the place for the connections, and that looks like something that I want, but maybe we can look through further. So I can come here and also view this. No, I do not like this. So this is Keystone 500. Do we have something else that we can see? Let's see, Keystone. Yeah, this also looks like something for coin cell battery. Of course, if I come in here, you can see how it looks like. Okay, this is not really a coin cell battery. So let's continue searching for something that can give us what we want. Battery holder Keystone. you look at the 3D view, this looks like something that we can use, right? So you stick the coin cell battery in here and then it sits in there. So even though I do know a couple of names for the things that I want, usually as a beginner you have to do what I'm doing. That is why I'm doing that. So now that we found the footprint that we want to assign, all that we've got to do is to double click, and then you can see here that this footprint has been assigned to the BT1, which is the battery holder in our circuit. So now let's go to the LED, and because this is LED, we need to go and look for the LED, right? So there are SMD components, which is surface mount, and there is the true hole. In this PCB, we just want to make the true hole component. So SMD, the component sits on the surface of the PCB, and for true holes, there usually are holes in the PCB into which you insert the pins or the legs of the component. For simplicity now, I just want us to do true hole components. Okay, so we have this LED true hole here, and then there are also different, so it is telling you the different specifications of the LED. So usually when you are making a design, you know precisely what you want. All right, is it a 3mm LED, is it a clear top, is it a flap top, and all the other horizontal and different dimensions that you might be interested in. Let's see how this one looks like. So view selection, it gives you the footprint, but when you click on this, then you can also see how it looks like. So in the 3D viewer, you left click and then you move around to see it in the 3D space. So I have left clicked and I'm just moving around to see how it looks like in 3D space. Okay, and then you can also use the middle mouse button to zoom in and also zoom out. I think I like this, so I'm going to go with the 3mm LED, and then comes the resistor. And if you are paying attention, you can see that the footprint libraries are also named in alphabetical order, so you know whether you have to go up or down depending on what you are looking for. So I want resistors true hole, and then we come to these kind of resistors. There are also different dimensions of resistors, so usually you should know what you are going to use, and you get all of this information in the data sheet of your components. For now, it isn't so important, we just want to learn how to, but you can always do the 3D view to see, okay, so this is how this resistor is going to be mounted if you choose to go with it. And there are different ones. So this is axial, and if you scroll down, there are different types. Okay, so there's the radial also. So let's see how this also looks like. Look at it. Okay, so learning how to choose the footprint, like I said earlier, is something that comes with practice. You can't learn it. It's impossible for you to keep in your mind the footprint that you need to use for every other component that you add. Okay, so you practice and then you get to remember them with time. So I'm just going to go with the second one, not because it's the best, we just need to make progress here. Alrighty then, so now that we have assigned footprint, if you come back and you click the footprint assignment, the footprint assignment tool, you can see that we already have them assigned. Another way you could do that was if you select a symbol and you press E, and the same edit dialog that we used to set the values, there's also the footprint thingy here. You can click on this and then you'll be able to select a footprint for that. So that's just another way. Kicad usually gives you multiple ways of accomplishing the same task. And so this is it about footprint assignment. Thank you very much for watching this, and I'll see you in the next video where we talk about a very important step known as the design rules check. See you there. Hello there and welcome back. So the very final step in the workflow, specifically in the schematic capture process, is to run what is known as ERC, or electrical rules check. And so if you look up here, there are tools, right? And you can see this icon. It's called electrical rules checker. And as the name suggests, the ERC analyzes your schematic to find electrical and logical errors before you create the PCB. Remember, the PCB is going to be created from the schematic, and every connection or every wire you draw in the schematic is going to appear as what is known as a rat net on the PCB, which you later use tracks to route. Okay, and so if there are issues in your schematic, it is going to be repeated in the PCB. So if you get something wrong in your schematic capture, your PCB is going to be wrong, and it's super painful. Imagine you live somewhere far away from China, which has become the manufacturing hub for PCBs, and you spent, let's say, 2 weeks designing a PCB, but you made a mistake at the schematic capture phase and you didn't know that. You've gone ahead to do the PCB layout and routing, which is difficult for complicated boards. And so after 2 weeks, you've placed an order. You've waited for 4 days for it to be finished manufacturing in China, and maybe one more week for it to be shipped to you, only for the physical boards to come and it fails every test. And this is what the ERC prevents, right? So it checks that your circuit makes sense electrically based on the symbols and their pin types. Some pin types are input, some pin types are output. So it's going to check. So some of the common checks include unconnected pins, right? So it's going to find pins that should be connected but haven't been connected. I'm going to let us run it, but I'm just explaining. And then there's also conflicting pin types, like it detects invalid connections such as two output pins connected together, right? And then missing power connections. It warns if power pins are not connected to a power source, right? So the pins on your symbols have pin types. There's the outputs, the input, and then the power pins and different types. And so it's gonna check to ensure that your connections are logically correct. Okay, it's not a simulator, so it will not confirm the physical correctness or the operational correctness of your circuit, but as far as the logical correctness is concerned, it is able to detect common issues. It's also going to be able to detect undriven nets, that is fine signals that have no source driving them, missing drivers, that is identifies nets that only contain input pins, power flag issues, that is once when Kicad cannot determine that a net is usually powered, right? So these are some common things in this particular circuit that we have. I expect that we get some errors, and it is deliberate. I left them out so that we can see how the ERC identifies errors and is able to suggest how to fix them. Okay, so again, there are options. Are you only interested in errors, warnings, exclusions, or you are interested in all? You can just select all. Very important. And this delete all markers, that is, if we had already run ERC and it found issues, it's going to put markers where the issues are, so we can delete the markers or when we want to rerun, right? So like I told you, I knew that there are going to be errors in this circuit that we have made. Not from the operational perspective. This is something that Kicad requires, right? So read it. First of all, look at where it has placed markers. It has placed a marker here. A marker is this red arrow here. It is telling us that there is an issue here, and it is also telling us that there is an issue here. And look at it. If you double click, it will highlight the particular area where the issue has been reported, right? And if I double click, it will come to the next one. Sometimes you get many of these and you have to fix all of them before you go on to design your PCB. So let's see. It says error, input power pin not driven by any output power lines. You know, this thing it is asking for confuses a lot of people. I also faced the same challenge when I was getting started. Like, this is a battery, and we all know that battery provides the voltage that drives energy around the circuit to get it to do its work. So what is it talking about? Let's read the error again. It says input power pins not driven by any output power pins. The reason is that these battery the pins on the battery have been defined as input, and so our circuit seems like something that should drive current around, so there needs to be that output thing. All right, now the solution is simple. It's a Kicad thing, and it's required. It has no physical bearing on your PCB. You just add it so that the design rules checker is going to be happy, right? So what you do is you come to the place power symbols, or you can also press the P key, which does the same, and then just search for power flag. Okay, so PWR power flag, this one. Just pick this, and then I'm going to rotate this and put it it can be right here or anywhere the connection is. Okay, and then I'm going to pick it again, and I'm gonna rotate, and I'm gonna put here, okay, where the arrows are. Okay, and then now let's go and run the ERC again, and you can see that there are 0 errors. So usually when you see this error about input not connected to any output pin, you know that you are missing the power flag. It is purely for the ERC checker to get its work done, and this is what makes people confuse it, and all the time they are adding these labels as I showed you in a previous video, but it is not entirely necessary. All right, so we have a complete circuit here, and what we're going to do next is how do we turn this into a PCB. So as you can see, I haven't spent time to take you through all the icons and all the tools here, but we are still making progress, and that is how learning should be. We learn the tool as and when it becomes necessary, because it is impractical and impossible for you to keep in mind all the functionalities of these tools while learning them in isolation. I hope you've enjoyed it so far. Thank you very much, and I will see you in the next video. Hello there, and welcome back. So we have gone through the most important steps in the workflow, starting from the title blocks, capturing schematic, doing the annotations, assigning values and footprint, performing the electrical rules check, and we are now at the stage where we can start getting into the actual PCB design. So in this video, I'm just going to show you how to switch over from the schematic and going into the PCB design. There are 2 ways actually, so always don't forget to save your file. They are not always automatically saved, so if you do not have the habit of saving, sometimes you'll be surprised that your hard work is lost because you didn't save. So just click on this diskette icon or the save icon here, and that is going to do the saving for you. So now that we know we have saved and electrical rules check and everything is working, what we can do is to click this icon here which says switch to PCB editor, open PCB in board editor. So we are going to move from the schematic editor into the board editor tool. Okay, and this is where having multiple screens become very important. Okay, so at this moment it has appeared on my other screen, but I have to pull it and bring it here. Okay, so I can actually minimize this and just show this. So this is the board editor tool. In many aspects, it has some resemblance to the schematic editor. Like, they have that resemblance between them, like in terms of layout and how to access the tools and how to operate them and all that. But the PCB editor is specifically designed with tools in place for creating the physical board, whereas the schematic editor is designed with tools in place for capturing the schematic. Okay, so you might ask yourself, we clicked on that icon to switch to the PCB editor. Where are the components, where are the footprint and all that? Right, so that icon launches the tool, but you still have to come up here. You see this icon here, and then you click update PCB from schematic. Okay, so what it means is that these two tools stay in sync with each other. So even when you have started designing the board, if you feel like making any change, you can go to the schematic editor, make the changes there, and then once you switch over to the PCB editor or the board editor and you click this icon, it's gonna update the footprints or the component on the board to reflect the changes that you have made in the schematic editor. So I'm going to click this, and there is this, of course, Kicad is a tool of a lot of dialogues, and so you just have to read. So option is relink footprints to schematic symbols based on their reference designators. There's a self-descriptive. Maybe you want to make some change and you want them to reflect in the reference designator. That's fine. Group footprint based on symbol group. You understand that also. The most important thing is down here. Okay, update footprint fields from symbol, which is good, and then changes to be applied. So it's going to tell you all the symbols you have used and the footprints that have been assigned to them and whether there are warnings or errors. In our case, 0, so we can just click update and we click close, and then now these are the components. You can use the same mouse button operation, so middle to zoom out, so zoom in and zoom out, look at it, and then you can drop it here. So you can see that the wires that we drew have become what is known as the rat's net over here. Okay, and you can see there is still work for us to do. We need to do some work, especially in laying out the components on the board and also doing what is known as an edge cut. But before we can do all of that, I need to explain some key layers of the PCB here and what you can do in each one of them. Of course, I'm not going to go through all, I think 15 or 16 of them. No, I'm going to go through the important ones, and then as and when they become necessary, I'm going to explain that. But just so you begin to feel happy about the progress you've made so far, even in this rough state, what you can do to celebrate your victory or the progress is click on this 3D viewer, and it's going to bring your PCB in 3D form, and you can see this is an ugly layout, right? This is not how we want to do things. And you might wonder, why is everything yellow? Everything is yellow because they are all selected. If I click outside to unselect them and you come to the 3D viewer, you can see I can zoom in and zoom out, and I can also use this mouse, the left mouse button, to move things around to look at it in 3D. So you can see that some of our components are surface mount and some of them are through hole. Look at it. The battery holder is a surface mount. The parts for making the connection, the electrical connection, sit right on top of the board. But for the LED and the resistor, you can see that they are through holes because there are holes from the top layer to the bottom layer. Maybe as an exercise, when we are done with the routing and everything, you can also practice how to turn this board into a completely surface mount board. That means you have to change the LED to an SMD LED and also the resistor to the SMD resistor. Okay, so this is just a brief overview of the board editor and the simple things you can do in it. In the next videos or the subsequent videos in this chapter, we are going to learn a lot more about this PCB tool or the board editor tool, and then we are going to finally lay out and route our simple hello world PCB. Thank you very much for watching this, and I will see you in the next video. So one of the first things that you need to do in the PCB editor is to come up with the edges of your PCB, right? So you basically have to define the outline of your PCB even before you arrange the component. Of course, some people also arrange the component, and when they finish, they define the outline. But the advantage of the first approach, where you define the outline before arranging the component, is sometimes you already have a given size, which is a constraint that you have to conform to, especially when the case in which your product is going to be packaged has already been designed. Then you don't have the liberty to design the PCB's physical layout to have just any shape and any size, right? So in that case, you have to ensure that you are creating your outline first, and then you do the arrangement to fit onto the outline, and of course respecting all electrical rules that must be respected. So like we did in the schematic editor, here also I'm just going to show you the tools as and when they are needed, right? On the right hand side, you can see that there are layers. As you know, a PCB, even in the physical sense of things, is made up of layers. At the very least, there's a front copper layer, which is the top layer of copper that we do our routing on. There's a bottom copper layer, and then there are all of these other layers in there. I'm going to talk about the layers as and when we need them, but in this video our focus is on the designing the edge. So that happens on the edge cut. So this is the edge cut, right? You can either double click to select it, or you just single click to select it. You can also come here and then you can change the layer that you are working on. So if I select the front copper layer, how you know you are working on a particular layer is you will see this blue icon on the left side of the layer. That tells you that whatever changes you are doing is going to have effect on the particular selected layer. So the same way I selected the edge cut layer from here, assuming it was in front copper layer, I could come here and then I can still look for edge cut, and that brings me to the edge cut. Also, the color of what you are doing is going to reflect the color scheme that is used for that particular layer that you are working on. Okay, so now that we are in edge cut, we have to learn about the tools that we can use to define the outlines of our PCB. At the moment, we haven't defined any outline, and so when we do the 3D viewer, it's just the PCB editor doing its best to give us an outline such that it contains all the components in our circuit, right? So what we're going to do here is, these are the tools that we can use. We have the rectangle, we have the circle, we have the polygon, and we also do have the Bezier curve, right? We're going to learn about these primitive tools. So I'm going to select the rectangle, and I can draw a rectangle. You click one corner, and you don't need to hold to drag. You can just click, release, and then drag until you get the dimensions that you want. At this moment, the dimension is also important to me. I just want us to have a rectangular outline. So if I do this, right, and we go to view, you can see that now we have our board, but the components are not there. This is because now look at where the components are hanging. This is because now we have defined our edge cut, so it's our work to move these components into the outline that we have defined. But before we do that, I'm going to show you how you can add things like fillets and chamfers and also dog bones. Okay, so with the rectangle drawn, if you want to add fillets, that is rounded corners to it, what you can do is you just right click on it. You just have to use the select tool. You select the rectangle that you've drawn, you right click, and then we are looking for shape modification, and in here we can either do fillet lines, chamfer lines, and also dog bone corners. Let's start with fillet lines. So here you just have to define the radius that you want to use. Let's say I want the radius to be 2. You click OK, and you can see that the corners of your rectangle have become rounded. If you're not seeing it well, we can do it again. So shape modification. Now let me just undo what we did. So undo is Control Z, like in many software packages, and then you go to shape modification, fillet lines, and I want it to be very clear, so I'm going to use 5 here, and then now you can see that it has rounded corners. And if we preview it in 3D, you can also see that indeed the board now has some roundedness to its corners. Okay, so that is it for fillets. Now I'm going to show you how to do chamfers. So I'm going to do undo to remove the fillet. You select, right click, you go to shape modifications, and we go to chamfer lines, and I'm going to do it 5. You will form an intuition of for yourself what chamfers are. So chamfers are like this, and then fillets are curved. This is easy to understand if you already are involved in 3D modeling. These things are common terms. So now you can see that there are some chamfers at the corners of the outline of our PCB. All right. Okay, so now let's undo this, and let's also see what the dog bone edges also look like. So I right click, go to shape, and then I go to dog bone corners. And in here you can see the dog bone dialog has come. You also specify the arc radius that you want to use, and then you add slot in acute corners. Okay, so look at how the dog bone, it looks like that toy bone that you used to keep your dogs entertained, right? So this is what is known as the dog bone corners. So if I do this, you can see that the PCB now has that shape to it. Another thing that we can do, I can actually delete the entire drawing on the, I can delete the entire drawing on the edge cut. And if I do this, what it means is that we go back to where we started from. It means now we don't have any distance to itself. We do not have any outline defined for our PCB. So this is it about how to define the edges. In the next video we'll learn some more, and then we can start routing our PCB. Thank you very much for watching, and I will see you in the next video. All right, so let's learn how to use the circle to also define the outline, right? So sometimes you want your PCB to have a circular outline, and it's just as simple as choosing the circle tool, clicking, and then defining a radius of interest to you, right? And so I'm just choosing these sizes arbitrarily. Once I do this and I go to the preview, you can see that we can have a round PCB outline. Okay, now the requirement is that the outline should be a closed shape. So what I mean is, if I should draw another circle at the center like this, then this area is what becomes the outline. So at the center there's going to be a hole. Let's review it so that you see. So you see, so you at liberty, it all depends on your own drawing skills and your imagination, but you have all the tools. You have the circle, you have the rectangle, you also have the polyline or the polygon, which will help you draw any arbitrarily shaped outline. So I can click this, I click here, I click this, I click here, I click this, I come here. I don't know why anybody will need a PCB shaped like this, but the only requirement is it has to be a closed shape. So I have to make sure I end right where I started, and that's what I'm looking for. So this is where I started. It snaps there, you click, and then you have that closed shape. Okay, so with this closed shape I should be able to preview, and you can see that indeed we have that shape for ourselves. So this is it, all you need to know about drawing outlines. In the next, we'll talk more about some setup that you need to do before we start doing routing. Thank you, and I will see you in the next video. All right, so before we talk about routing, we need to talk about the basic board setup that we need to do. All right, and so to do that, you can click on this icon here. It's called board setup. I'm sure you can also find it under files and board setup. Okay, so it brings up this dialog here, and the areas of interest are the physical stack up. So when you click the physical stack up, this is where you are defining the physical stack, right? The layers of the different layers that are in the PCB that you actually want to design. And one of the very important things is how many copper layers are you interested in, and see what you can do with Kicad. You can have all the way from 2 all the way to 32 copper layers. All right, so it depends on the complexity of the PCB that you are designing, and of course also it depends on the capabilities of the manufacturer that you intend to use to manufacture your PCB. This is a very simple board, so two layers is okay, and then it will show you how it is stacked up, and you can also define the thickness of the individual layers depending on the capabilities, but usually these default are okay. All right, and then the next thing you want to do is you come to constraints. This is very important. These settings here, the default values are also okay for at least two of the most popular manufacturers from China, PCB and JLCPCB. But sometimes you want to modify them to match the exact capabilities, especially if you want to use the capabilities of the manufacturer to the best of their abilities. Then you want to modify these things. So you might ask yourself, how are you going to find these values that you need to put here? Okay, you just have to go to Google and then Google for the manufacturer's capabilities, and you usually find a link. So this one, I googled JLCPCB capabilities and it brings me to this page. It is telling me they can handle from 1 layer all the way to 32 copper layers, and then they are giving you different values and figures that you can set for different constraints, things like clearances, thickness, track weights, and all that. Okay, so you just have to come to the capabilities page and look at what is possible. So for traces, for example, you can see minimum track weight and spacing and clearance and whatnot, tolerances and all that. This is just the capabilities of their machines. So if you want to manufacture with them and get the best result, you need to make sure that you are setting these values to be within the values that are acceptable by the manufacturer. And in here we can also see the capabilities for the PCB manufacturer. Similar information, you just go through, you see the values, and then you enter them there. But like I said, for this very simple board, the default values are okay. I'm just showing you so that you know how to change these things. Okay, there are other things like predefined sizes for track sizes, like when it comes to routing and all that. We also come here to take a look at it. So this is just how to define the capabilities. In the next video, we'll actually now use the knowledge we have to draw the board outline, do the layout, and then we can start route and see you then. All right, so let's talk about the board layout, and then we can do our edge cut. I told you in a previous video that it's usually better to start with the outline. That is, you define the outline on the edge cut before you do the board layout. And this only applies when you are working within the constraint of, let's say, a case that have already been designed. This is very simple and we are learning, so I'm going to let us do the opposite. We are doing the layout, and then when we finish, we'll draw our board outline around it. Now, the key focus of the key focus when it comes to laying out your PCB is, first of all, laying out the component in such a way that routing is going to be easier, right? So you want to lay them out in such a way that you have very minimal wires crossing. Now, these thin wires that you see here, they are called rustnets, right? And they are the equivalent of the wires that you drew in the schematic capture. In the PCB editor, seeing this rustnet doesn't mean you have routed. It's only telling you that you need to actually do a routing. You need to route copper between this point and this point, copper between this point and this point, copper between this point and this point. It doesn't necessarily mean that you have done it. It's just a signal. It's indicating that you need to actually do the routing. And so the first thing you want to focus on is, how do I lay out my component in such a way that it is easy for me to route and there are fewer wires crossing? Because every wire crossing means you might have to use VS or your routing becomes really complicated. But this shouldn't be a complicated circuit or board to route at all. It's a very simple hello world setup, so we shouldn't struggle with it. After you have optimized for routing, then of course you also want to optimize for aesthetics or beauty, right? A PCB is also a work of art, so As much as you lay out to make sure that routing is easy, you also lay out to ensure that it has some beauty to it. And these are things that you can only learn with practice. No number of hours spent in a video tutorial is going to teach you routing. That was one of the mistakes I made when I was getting started. I thought there is that video I can watch that will make me a master of routing, but I learned the hard way that the skill set grows the more you do routing yourself. So let's do it here. Sorry. So our battery, I think is placed okay. I can select the LED and then you press M to move it, and you can see that it's kind of suggesting to you how we can actually lay this thing out. It's so simple, right? Look, for the resistor, and again here too, when you are selecting, make sure you are clicking on the component itself, because I can also click the designators like the R1 or the value and move them around. It's all part of the aesthetics or the beauty thing that I spoke about, right? So here I have made sure I've selected the resistor itself. Otherwise, if I select, let's say, the designator alone, and sometimes when it's confused, it is also going to ask you which one you want to select. So you just click this and I press M, and you see that I can move it to another place, right? So I'm going to get to the center of this M to move it, and I just want to make sure it is somewhere here. This is not a very complicated PCB to route, so we are not going to spend so much time here. Now let's look at this. If you look critically at this LED, you can see that we need to rotate it, because this rat net here is coming all the way from here and it's getting into this one, right? You can see this is net D1A, right? And then let's see what is also here. This is net D1A. So it is better we position this such that this net and this net are facing each other, right? So I can select this and the same shortcut, and you can see that now they are perfectly aligned. So if I zoom in, see net D1A is here, and then net D1A is also here, and then it also helps the ground to be aligned. So this is ground and this is ground. So these are the things that you want to look at in terms of layout. And at this point, using the windowed crosshair is also useful, because it will help you to know when components are perfectly aligned, right? So I can select this, and then I want to align it both on the vertical with this side, and also on the horizontal with the resistor, right? So if I do this, I think it looks quite okay. This is so simple a board, we shouldn't struggle routing it. But like I said, practice, we will do some more complicated routing so that you learn some more skills. And also you want to optimize for spacing, because when it comes to manufacturing, the bigger the more you pay. But you also want to optimize for spacing, respecting electrical rules and constraints. All right, so you just have to use your understanding, and also your understanding of electronics and what is required, and also the aesthetics, the beauty that you want to achieve. And it's a combination of all of these that gives you a functioning PCB that is also beautiful and nice to look at, right? One other thing I want to show you when it comes to layout is, you see, for every component there is this outline around it. It is called the courtyard. This is an absolute constraints that you must respect. Never let the courtyard of one component cross into the courtyard of another component. If you do that, then you make it impossible for the place and pick machines at the manufacturer's end to be able to do their work. So apart from fabricating the PCB for you, the manufacturers also have robots that can actually pick the component and put them on the board that has been fabricated and actually do the soldering for you. If you do not respect these courtyards not having to cross into each other, then you will make it impossible for those robots to do their work. I think we can move this up a bit, because we are not crossing anything, and there will still be space for us to route. And then we can also move this here and ensure that we are aligning it nicely. So this is where the crosshair thingy comes in, and it looks very nice. Of course, the space between the courtyard here and the rat net here, which will later turn into a track, is determined by the clearance rules that we have set. And of course, this also has some design rules check that we have to run the same way we did for electrical rules check. The PCB editor has design rules check that we can run later to see if there are issues with our PCB. So this is it about the layout. Now that we are done, we can go to the edge cut here. And then what we're gonna do is to just define the outline of our PCB. This is a very simple PCB, so let's make it a rectangle, right? So I'm just gonna put it here. So you see that in this case the crosshair thing really helps, right? So I click here and then I come all the way here, and I think this is okay. Yeah, I think this is okay. So what I can do now is I can just give some rounded corners like we learned how to do. So shape modification, fillet, and 5. I think 5 is a bit too much. So I'm going to select again, right click, shape modification, fillet, and let's do 3 or maybe 3.5. I think 3 is okay. So now I can save this, and then I can come to the 3D viewer, and you can see that this is not the best layout. There's too much space being wasted. These guys can actually be close together, but I mean, this is our first hello world, so the objective is just for you to learn how to use the tools. Later we will learn how to apply aesthetics and do better routing. So thank you very much for watching this. In the next video we'll start talking about routing. All right, so let's route this simple board. But before we do, I want to show you something. If you zoom in, you can see that we are seeing the reference designators twice for some of the components, right? So we can see D1 here, and we can see D1 here. We can see BT1 also here. And it might be challenging for you to wrap your head around, and I'm going to explain that. But before I do, let's view this in 3D, and you can see that there's only one of them showing, right? So there's D1 here and there's BT1 here, even though in the PCB editor some of them appear twice. Look at it. So here we see BT1, D1, and also D1 hiding here. And what you are seeing is that one reference designator on the front silk screen layer, right? So I'm looking for the front silk screen layer, this one. You see that when I hide that layer, this one goes away. All right, so what happens is the front silk screen layer is intended to be printed on the PCB, as we saw. So the silk screen layer is just the layer of the PCB where we can actually write things. So it can be the reference designators or the value. Like even here we can show the 470 ohm here for when people are doing manual assembly, right? We can also show the 5 volt. And so the silk screen layers are two, the front and then the back, and they are intended to be printed on the circuit board. Okay, and so if I click to hide it, you can see that it goes away. The fact that I've hidden it here, look at it, if it has any effect. It doesn't, because it will still show on the PCB. This is just hiding it so that it looks less cluttered as we work on it. And then there is this, so let me show this one back. You just click the eye icon here. That is how you hide or show. And the other reference designator, which is the one in here, the D1 that is hidden all the way in here, is for the fabrication layer, and it is intended for assembly of application drawings and documentation. So if you think it is getting in your way, you just look for the fab layer and you turn it off, and you see that it goes away. And it helps, like for really complex circuits, it helps that you declutter your space. This is a simple board, so it might not be an issue, but many times it helps to do that. Okay, so you can click the zoom to fit so that you are using the area well, and then now we can start the routing. Always make sure you are doing the routing on the right layer, the correct layer. At the moment we have selected the edge cut layer. You can see it from here, or you can also see it from here. We want to route, and this is the top layer of our PCB. That's what I mean. this is the top layer, right? We want to route on top. The reason we want to route on top is that if you go to the back, you can see that our battery doesn't come, the terminals of our battery doesn't come all the way through the board to the back, and this is known as surface mount. So the terminals for connecting them to the PCB is actually sitting right on the face of the PCB. Okay, so that we want to do routing on the top here. Of course, we can also route and then place VS and all that. I will show you all of that, but for this particular session, we are just going to use the surface mount kind of routing. So we are routing on the top. Okay, so we have to go to the front copper. This, you double click it, or you just single click, or you can also select this drop down and then choose the front copper. They do the same thing. One key thing is that the layer on which you are, or you've selected, determines the color in which things are going to show when you do them. Okay, so now that we have selected the layer, the next thing is we need to turn that RASnet into a track, and you select this. So you can do routing, you see there, you can do this. We will talk about it differently, but we are doing single route. So you just select the single route. If you click and hold, and then you come to the one you want, you just click on it, and that is it. Now here, usually you should be able to select the sizes of the track width. That is if you have predefined some, but when we went to the board stack up, we didn't define any, so it's going to use the default, which in this case is okay. We will get to the point where we define our own track weights for different purposes. For example, if the track is supposed to be carrying large current, right, because the size affects how much current it can also carry, so it becomes important during those times. But now it's okay, this is just an LED that we want to turn on, so let's not disturb ourselves with it. So I just click this, and then you see this RASnet here. I can just click on this ground here, and then I come here. Okay, I'm doing this on purpose. We can actually do what is known as a copper pour to eliminate the ground connections before we do the routing, but I'm letting us do this on purpose because we have a video where we talk about the ground pour, copper pour, and then after that we will do the correct thing. So you see that now that RASnet is gone, right? And then I see that there's a RASnet between this line and this line. Okay, if at this point the crosshair thingy is getting your way, you can get out of it by just going to this one and making sure that the route tool is selected, single route, right? So I can click on this and I can just drag all the way here. That also connects them for me, and then I can click on this and I bring it all the way here. So now you can see that our board is fully routed. I can save this, and then we can go and view in 3D, and you can see that indeed there are physical wires connecting the individual components. So this wire comes from here to here, and then there's a wire that comes from here to here, and there's a wire that comes from here to here. Because we routed on the top, if you go to the bottom, you won't see any wire. The thin one that is passing through is just a shadow of it. It's not actually on the bottom, right? So you can see that we have routed in here. So this is it about a simple routing. It is not the best way. I will show you some other things you have to do, but of course I need to teach you in stages. So thank you, and I will see you in the next video. Hello then, welcome back. So in this video we are going to talk about copper zones or copper pours, specifically ground pours. If you look at this PCB, you can see that large surface area of our PCB is unused, right? And we only have these 1, 2, 3 wires interconnecting the components on the board. While this is okay, I mean, for this simple circuit it works, usually we want to add what is known as copper pours, and I'm going to explain why we do that. So copper pours, which are also known as copper zones, they are areas of copper that automatically fills unused part of the PCB and connect to a specific net, such as the ground, or in this case we can also choose the 5V. And by the way, ground pours are by far the most common because they provide several important electrical manufacturing benefits. So what we want to do is we want to fill all of this unused area with copper that is connected to the ground net, right? We want it to connect to the ground, and it has some electrical advantages that I'm going to explain. So the first one is that it lowers ground impedance. So instead of every component having a thin track back to the ground, they all connect to a large sheet of copper. And in fact, in many cases, if the circuit is complicated, one of the ways for reducing the complexity of routing is pouring your ground copper pour first, and that eliminates all ground connections. So what it means is that after doing the ground pour, every pin or every net that is connected to ground is already eliminated, and you only have to route rat nets that are not connected to the ground. Other advantage, the second advantage is it provides a better return path for current. So like if you pour ground on all unused places, and what it means is that every other component that has to connect to the ground has a shorter path to ground instead of going through a longer cable, okay, or wire routing. And remember, at the PCB layer, what is long is relative. It's not in the same sense as what is long in the physical world, but things can be long and they don't have to be. It also provides easier routing. That is the third reason. So instead of drawing a separate ground trace to every component, you just pour copper to ground, and that eliminates everything that has to connect to the ground. We also have heat spreading. You know, PCBs are carrying current. These tracks on the PCBs are carrying current, and they do generate heat, right? This again is a simple hello world thing, so we didn't see it, but in a complicated board, heat is generated. And when we do copper pour, especially the ground pour, it acts like a heat sink. So some of the heat from the component that get heated will have a large surface area to distribute the heat, and it also reduces EMI, right? So that is electromagnetic interference. So a solid ground plane helps to contain electric field. So what it means is that there's going to be less radiation from the PCB, there's going to be better immunity to external noise, and easier EMC compliance. And also there are some manufacturing advantages, such as removing large areas of bare fiberglass and replacing them with copper, because in the manufacturing process, after they have made the route, they have to etch away or eat away all the copper in the places where there are no copper. But if you do ground pour, then you are making the manufacturing process a little bit easier. So I'm going to just end this video here, and we'll use it as an explanation for why copper pours, and in the next video I will show you how to actually create those copper zones. Thank you, and I will see you in the next video. So before we learn how to create copper zones, we want to delete these tracks that we have already routed, and there are many ways of doing that. One way is to go to edit, and then you are looking for global deletions here, and then you are selecting the things you are interested in deleting. We are interested in tracks and vias, and you can check these settings to see what makes sense, and then you click OK, and you can see that all the tracks that we routed have gone away. So now if we preview in 3D viewer, you can see that there are no tracks in there. This makes the way for us to learn how to do ground pour or copper zones before we do the routing. So I'll see you in the next video where we do that. All right, so now let's learn how to create the copper zone and connect it to the ground. Always remember to be in the right layer, and we want to do this on the front copper layer, so that is selected. On the right side here, you will see this called draw filled zones. This is how you create copper pours, okay? So I'm going to click on that, and then I want to just position in the correct frame, and I can click. You just want to pour the copper in all the areas, in all the areas where you are not going to do routing. So usually you want to do it around the outline, okay? There are cases where you also want to create copper zones inside the PCB itself. We'll get there. Sometimes you want to connect all nets together, especially power distribution and all that. But for now, we just want to pour copper all over every space that was going to be empty. And so we are going to do that from the outside of the outline. I think here the crosshair thingy is going to help, so that I know you don't necessarily have to precisely select the correct outline, right? The tool knows where the outline of your PCB is, and so it will know where to apply the copper pour. So don't sweat it too much. So you click, and then here you have to select the net to which it has to be connected, right? The pour has to be connected to some net. Usually we connect it to the ground. I have explained the advantages in the previous video, but there are also times where, because of power distribution, you want to connect it to, let's say, your VCC. You can also select that. Now we just want to do ground pour, and then in here you want to set some of these settings. These are important. There are pad connections. It determines how the pad, so in this case, this, this is ground, this is ground, so it's going to determine how the pins, or the pad, that is the place where you do the soldering, is going to get connected to the ground pour that you are doing. We'll have a time where we will explain the different options here, but for now it's okay to choose thermal relief, and I'm sure by the name you know that it has something to do with heat distribution. All right, so you click OK. So now that I have selected it, I can go in here, I come here, I click. It also has to be a closed shape, right? The same way you draw the outline of your PCB. So I click here, I do that, and I will come here, and you can see that here the crosshair is helping me to know when I'm perfectly aligned with the previous point that I placed. Now I can zoom in just to be sure that I am locking at the right point, and look at it. So now if I come here and it is perfectly aligned in here, the question is, okay, we see something here, but where is the copper zone that you have drawn? And that is where pressing the B key on your keyboard is what is gonna show it. Okay, so now I can save and then do the 3D preview, and you can see that we haven't routed yet, but you can see that previously all this space was empty, right? The copper there would have been etched away in the manufacturing process, but now you can see that there is copper there. All right, and so we'll route through it. It will remove part of this copper, but it will still maintain the ground connection. And you might be wondering, how is the ground connection done? Look at it. You can see that this pad here is connected to the ground. So look, there is a connection from here to the pad. That is how the ground of the battery is spreading across the entire PCB. And if you look at the LED too, you can see, let me position it well, you can see that the ground side is also attached to the ground. So automatically the ground side of the PCB is connected to the ground side of the battery. And what that means is that we don't have to route from here to here. You get a point. So in teaching about the advantages of ground pour, I mentioned that it gives a shorter path to ground. So instead of drawing a track from here to here before current can return to the battery, it's just here, and the whole board is literally connected to the ground. So any other area that should be connected to the ground by now is automatically connected. So you can see that now we just have to route to tracks, and our PCB is better than the previous one. So let's do that now. Now that we have done this, you can see that the rat net that used to be between the ground pin of the LED and that of the battery is gone, because that connection is automatically established by the ground pour that we have done. They are electrically connected at the moment. So the only rat net that we are seeing is this and then this. So let's go ahead and let's go to our routing tool, and then let's just route from here to here, and then we route from here to here. And it might confuse you. Okay, I've drawn this, but it looks like you've drawn this net, or you've drawn this track in the ground. You have to press the B again so that it will refresh itself and ensure that it is redrawing it. So now you can see that there is a gap between the track and the ground, right? And the ground connection is not broken. Look at it. You can see that there is that continuous area of ground pour all the way from here to here, all the way from here. It comes all the way here. It continues from here and all the way. So now we can just preview again. we preview again, and you can see that this is a better routing that we have done. Okay, so look at it here, and it looks beautiful, and it is electrically better than what we did previously. And this is it about ground pulse. Thank you very much for watching, and I will see you in the next video. All right, so just as we had to run electrical rules check in the schematic capture phase, when it comes to the PCB layout itself, we should also do what is known as the design rules check. It is similar to electrical's rules check, just that this thing is checking for the design of the PCB. Are we respecting the clearances that we set between different tracks and all the capabilities of the manufacturer that we put in there? All right, this is a simple board. It's likely we wouldn't get any DRC. So what you do is you come up here, you look for this tool, design rules checker, you click on it, and then you just click on run DRC, and if everything is okay, it's gonna tell you errors 0, warnings 0. If you have issues, you have to make sure you correct them. Otherwise, this is how you will still ship your PCB to the manufacturer. They will design it, they will bring it to you, and then by the time you are ready to test, you realize that things are not working. Like I said, this is so simple, you shouldn't have any design rules issues. But if you like, move let's say the LED such that it courtyard gets into or collides with the courtyard of the battery or the resistor, and then see what's gonna happen. Learn by practicing. Okay, so just about the DRC, in more complicated PCBs we will have issues, and then I'll show you how to resolve them. Thank you, and see you in the next video. All right, so now I want us to talk about mounting holes. So usually your PCB is going to be fixed to a case, right? And then there needs to be some fastening between the PCB and the case. Many times it is going to be through the use of screws, and so we need to create holes in our PCB that is going to be used to fasten the PCB to whatever case or container it is contained in. All right, and to do that we can manually use the circle to draw holes in here. Remember, the outline of your board is supposed to be a closed shape, and so if you draw something inside of it, that thing becomes a hole, right? We demonstrated that in a previous video. Now remember, we are doing this on the edge cut, so always go to the edge cut layer, and then you can come to this add place footprint here. The shortcut is also the A, just as we do in the schematic capture. And then what you want to do is to search for mounting hole. So there are many predefined mounting holes for you that you can choose from. Okay, and so let's say we want to fasten it using an M2 screw. There is already the M2 mounting hole defined for you, and the details of it is also here, so you can click and then you place it wherever you think is appropriate for you, right? So now that I've done this, I can also, you can place more, right? So I'm going to press the A key again, and I'm going to search for mounting hole again, and the M2 that I recently used is gonna come here, and I can also place that somewhere here. It all depends on how you want to fasten it, but I just thought I should show you this. So if we go to the 3D view, you can see that the hole has been created across the vertical of the PCB, so you can insert an M2 screw here and then screw it or fasten it onto any fastening surface that has been made. Thank you very much for watching this, and I will see you in the next. So after adding the mounting holes, I see there's going to be an issue here with the designs rules checker, and so I want us to take advantage to see how to fix such issues, right? You can see that clearly the reference designator for this mounting hole and this, they are sitting outside the outline of the PCB, and that is a problem. So let's run the design rules checker and let's see what we're gonna get. So it's giving us warnings here, and it's warnings because it doesn't affect the electrical operations of the PCB. So here it says arc on edge cut, reference field, blah blah blah. So it says silk screen clipped by board edge, and you can see that this ref is supposed to be written on the silk screen, but you can see it is sitting outside the boundary of the edge cut, and so that is definitely a problem. So what we can do to fix this is I can select this, I click M to move, and then I just move it to a place where it doesn't cross the outline. I can also select this, I press M, and I can move it somewhere here. I can save that, and we run the design rules checker again, run DRC, and then now you can see that the warnings are gone. So take your PCB design so seriously that even if it's a warning, you want to solve it. Do not say, okay, I can ignore warnings and I'll only focus on errors. Aim for 0 warnings, 0 errors. It's not always possible, but as much as possible, try your best to do that. I will see you in the next video. So before we learn how to export your PCB for manufacturing, I want to show you how you can add some branding information to your PCB, and that has to go on the silk screen. It depends whether you want it on the front or you want it on the back, and this could be an image that is the logo of your company, or it could be a text. Now I'll just show you how to use text, and I want us to place a text on the front. Okay, so I'm going to select the front silk screen because that is the layer for adding text and labels and all that to the PCB. Remember, I said I'm not going to show you all the layers in one go. I'm going to bring them up as and when they are necessary. So at this point, make sure you are on the front silk screen, because all of these D1, BT1, R1 ref, they are on the front silk screen, and this is how you know they show up as white. Okay, so we just want to add something. So here I can click on the test, and then because we have selected a front silk screen layer, it also has been the layer that is selected here, and I can type in whatever I want to type. So I'm gonna call this mechatronics with pi, right? Mechatronics with pi, something like this. You can play with the font, whether you want it to be bold, how you want it to be aligned, whether it should be right aligned, centered, left, the vertical alignment, whether you want to mirror it. All of these settings are there. Just play with it. You click here, and then now you are free to drop it wherever you want to drop it. So I want to drop this thing here. So this could be the name of your company, it could be the name of the product, whatever. It's just branding information, and you are free to type whatever. We could also use images. We have to convert the image to a specific format. I will show you all of that later. So you save this, and now we can go to the preview, and you can see that we have our branding information nicely sitting here, mechatronics with pi. If we had added it to the back here, we would have to mirror it or invert the direction so that it will appear at the back, and I'm going to leave that to you as an exercise in this video. So try to add some branding information at the back. Maybe it could be the name of the product, the version, and also the company or the author that is working on that. Very simple, right? Thank you, and I will see you next. Okay, so all too soon you started from not knowing anything about Kicad to the point where you have your super shiny PCB designed. You are ready to place an order for manufacturing, but the question is, how do you get the files that are necessary so that the manufacturer is able to manufacture your PCB for you? And that is what we are going to learn about in this video. So make sure you have saved your PCB so that every changes you've done is exactly what is recorded in the project. And the next thing you want to do is you want to come here and you see the plot icon. Okay, most of these things you can access them in multiple places. So if you go to file, you can see that you also have plot in here. So you can either click file plot, or you can directly just click on the plot icon. The plot icon here. Okay, so again, here, do not change things unless you know exactly what you are doing, or you have watched the full course and have explained when to include something or to remove it. But the default is okay. This is a 2-layer PCB. So the front copper, we needed the back copper, the front paste, the back paste, the silk screen, the mask, the edge cut. You know, all of these are important. For example, if you remove the edge cut, the manufacturer will not know the shape or the outline of the PCB that you want. So these are all containing valuable information that you want. and there is also the format here. There is the PostScript, SVG, DXF, and PDF. For manufacturing, Gerber is what most of them need, so it's okay to leave it at Gerber. And you also want to create an output directory into which the manufacturing files are going to be generated. It's going to generate multiple files actually. So you just click on this. It's going to take you into the project folder. What I usually do is to create a new folder, and I'm going to call that manufacturing. Okay, manufacturing. And it's inside this manufacturing that I want it to be generated. Do you want to use path relative? Yeah. So you click yes, and what you're gonna do now is to just click on plot, and this is going to plot the files that are needed in the manufacturing folder that we created, or in your case whatever folder that you selected that they be placed in. The next thing is, okay, we have generated the manufacturing files that are needed for fabricating the PCB, but for us to be able to put the component in the holes, for example, the holes for the legs of the LEDs and the resistors have to be created, and that is the drilling process. So we also need to generate drill files, and so you just click on drill files, generate drill files, and the output folder, I want it to be in the same manufacturing folder. Leave these as the default for now, and you can just click on generate, and this also generates a file with the extension .drl. That is what the drilling machines or the robot that handles the drilling are going to use. It could be a laser drilling machine or some other machine that drills using a different mechanism. What's most important is that the data or the files are there to guide it to do its work, and that is it for generating. In the next video, I will show you how to take a look at these files and actually use them to place an order on the manufacturer's website. See you then. All right, so let's take a look at the files that we have generated for manufacturing. If you come to the Kicad homepage and you see the folder we created, in my case I called it manufacturing. It depends on how you called yours. I can just right click on this and go to open directory in File Explorer, and it's gonna open it in the Windows File Explorer. So you can see that there are different kinds of files here. How you know that is to look at the extension of the file. So there's the .gbr, that is the Gerber files, and we also have the .drl, that is for the drill. You need all of these to be given to the manufacturer for manufacturing, and you can see that the Gerber files are generated layer by layer, and this is why it was important for us to select the layers that have to be included. This is it. In the next video, I will show you how to go to the manufacturer's website and upload these files to get our files manufactured for us. Thank you, and I will see you then. All right, so now you have the manufacturing output files created. I just want to show you how to place an order for your PCB on one of the most popular PCB manufacturers in China. This one is called JLCPCB. There is also PCBWay, and there are other options like Nest PCB. But I'm just going to go with a very popular one. You don't necessarily have to order from China, but I can guarantee you it's going to be cheaper, and they will do a good work. They will ship to you in a couple of days. Again, this is no sponsorship. This is just me mentioning them because I use them. So let's go to the folder where our project is. This is the Hello PCB folder. This is the manufacturing folder that contains the Gerber files and also the drill files that are needed. What you want to do is you right click, and you just compress it into a zip file. So it depends on your operating system. I'm on Windows, so I can just right click and say compress to and select zip file, but whatever way you use to create zip files on your operating system, that is what you have to follow. So I have this manufacturing.zip file created here. I will just drag it to a page on JLCPCB and have my PCB ordered. So I'm switching back to the place. So we are here on JLCPCB. You click on get instant code. Again, this site could have changed by the time you are watching, but I'm sure it's going to be the same flow. So they do many things apart from PCB manufacturing. They also do sheet metal, 3D printing, CNC milling, and all of that up here. So they are a complete company that you can deal with. So I have this add Gerber file here. You can either click and browse to select, or I will just drag the manufacturing folder and then I'm just going to drop it here like this. So give it some time. Of course, it depends on the speed of your internet connection, but it's not a big file, so it usually doesn't take a long time. Yes, so it says success, the file has been saved, and you can see that it is already beginning to make sense of the content of the zip file, right? This is the PCB that we designed. This is the front, this is the back. You can actually go to Gerber viewer, and in the Gerber viewer you can see that this is actually what we want. So in Kicad, what we saw had the 3D models sitting on it. So we had the battery holder, the resistor, and the LED. But this is not how necessarily the manufacturer is going to bring it to you. Sometimes they'll just bring you the PCB itself, and you have to do the soldering of the component on it, unless you tell them that you want to do the fabrication and assembly, at which point the content you have to give them is also going to be different. So their site gives you the ability to view your PCB in 2D, or you can also go to 3D, and in the 3D the same controls that you use in Kicad. So I left mouse, click, hold, and then I'm able to drag things around to see how my PCB is actually gonna look like. Okay, there is also the ability to view the bottom, or you view the top. All right, and you can also click on the order now. You literally have to specify some few configurations, like the color of the PCB. Do you want blue, red, purple, yellow, black, whatever? The seal screen, they are almost always white. Sorry. And then you can literally look at all of these options, but the most important thing is that you have uploaded the Gerber file, and then you will also specify how many copies of the PCB you need. And you can see that the site is updating itself depending on what you have uploaded. So it's gonna cost me $2 to actually get this done in 2 days. If you want it in 24 hours, it goes to 7.5, and this is 24 hours PCB only. And then look at it, the most expensive part is not the PCB manufacturing itself. Unfortunately, it is the shipping. So this also depends on where you live. So the shipping price is actually gonna be calculated on checkout. Unfortunately, shipping is more expensive than manufacturing this in China. And so guys, thank you. You started from knowing nothing about Kicad, and in just a short time you have created your first PCB and you have been able to place the order. Thank you, and I will see you.